welcome everyone, and welcome to another session of Coffee O'Clock, where in the first half an hour we have a guest speaker, and remaining 1 hour we discuss about the topic which the speaker gives a talk. And today we have Ludmila, and she is, I know her very personally because we are working together and at the same place and under the same supervisor. She did her bachelor's and master's from Brazil, University of Bremen. And I don't know, I mean, my spelling is very bad. I know, I mean, it's very bad, right? So, yeah, so she's going to present about quantum tomography, and it's actually, this is very interesting because she did, I mean, she dedicated her master's studies and the master's thesis in this topic. So she is, you can say, a master's in this quantum tomography, and she's going to talk about this continuous variable stuff and how the Wigner function behaves. I mean, I also don't have any idea, so I'm looking forward to learning from her. So please, the ground is all yours.
I share my screen. All right. Thank you, Akash, for this fabulous introduction. So again, my name is Ludmila Batello, and today I'm going to talk a little bit about quantum states tomography, more specific about continual variable states. What is this? What's going on? So first of all, I want to make a digression. I don't know about you guys, but I'm a kid up from the 90s. So I particularly used to like very, very much this kind of games. You can see a lot of pixels there. This is low quality for today's standards. But I think it's so beautiful how they could manage to deal with so little amount of information and make all these beautiful, very interactive scenarios and very fun games from this. So think about this representation of pixels and stuff. I want to just talk a little bit about this because, okay, we can have a distinction here about the discrete representation using, I don't know, bits like pixels in this case, and a continuous, like in the case of, I don't know, a draw with a pencil, when you slide your pencil over some surface, a piece of paper. But of course, if you increase the amount of information, increase the amount of bits or pixels you're going to use to represent what you want to do, it actually looks very, very similar, like pretty much the same. So how do you know something is something? You have to collect some information about it. But sometimes with just a small amount of information, you can already guess. You do guys, I think you already know what this picture is, right? It's obviously a Mona Lisa, right? So what's going on? What's the problem? I'm not here to talk about art or video games, not exactly, but it could be related. But I guess you guys want to know a little bit more about, I don't know, some quantum mechanics, physics, what's going on. So moving on, basically what, I don't know, physicists like to do is like, I don't know, make some experiment. We want to check something, some information, and we collect some data. From this, we have to deal with this data, right? It's just, otherwise it's just a meaningless bunch of numbers. It has to make sense. So a scientist like me have to deal with the data. And in the case, I was interested about what do you need to, I don't know, reconstruct to get information about the quantum state. So again, as video games, we have this discrete and art representation, music, whatever. We always have this discrete and continuous representations. This also happens for quantum states. In the case for discrete representation, like this spin up and down, or zeros or ones, you can represent like vectors in some qubit space, or density matrix. I'm going to talk in this in the future, or as continuous functions. And these continuous functions for quantum states, some of them live in a very special, I don't know, place. I would call this phase space. And the representation usually to, you know, represent this is also, is called Wigner functions. It's a very complicated function. Don't worry about this, guys. And for instance, like this specific state is called cat state. I like it very, very much because I'm a cat lady. As you can see by my shirt, there is some tigers here. Panthers, I would say. And it's a very interesting function because you can say, okay, this is a density, a probability distribution, right? But this is kind of weird because it allows some negative values. Usually probability distribution is not exactly like this. So actually this is called a quasi probability distribution. Sorry about my broken English, guys, because in Portuguese we say like this. Anyway, let's change this topic a little bit, okay? Just hold all the quantum information stuff. When you think about tomography, especially I think about this, like seeing weird stuff inside our bodies, our brain, or some kind of scanning. And yes, this is correct. This is a kind of tomography. Like it's this whole thing, tomography, is literally reconstruction something by slices, by piece, so you can achieve some very nice information about the object you want to analyze. And in terms of mathematics, what's going on is called something called random transform, which is basically some kind of projection of this function gives some amount of angles, and I would say binding of the function, like some position of this, I would say, analogous phase space. So you have basically pretty much like what we have for human scanning bodies, like projections of the function. In the case, the functions are on bodies, like the shape. And this is very nice because when you vary this information about the angles and rotate it creates really nice figures. It's called a Sonogram. There is a lot of information very nice on the web. We can discuss this later. But why I'm giving this importance to this? Why do I want to talk about this random transform and all this stuff? Because actually something similar can happen when you deal with, especially with optics, quantum optics. Quantum states with related, for instance, when you put some lasers and beam splitters and all the stuff. I'm a theorist, guys. If there is some experimentalists over there, help me. Anyway, in the case of quantum optics, the way people used to get some information about the quantum states is called Homodyne tomography. So basically you have some signal you want to identify and some, I don't know, coherent state. You already have some very nice information about it. You completely know what is going on. And this coherent state, you can vary the intensity and other properties. So basically you can correlate the intensity of this, I don't know, when you pass this through this almost a Mach Zehnder interferometry. Basically you have a beam splitter. There is some very fancy mathematics behind this. And you can get what we call quadratures, projections of the state on the phase space, measuring this. It's quite complicated. Don't worry about this, because the mathematical functions this is helped. You basically have to reverse how to transform, but this is very function, really hard to regularize. And this is exactly the same, I don't know, methodology to deal with the quantum states is the one to do with tomography. And for quantum states, it's something like this. Don't worry about the equations, guys. So seriously, but okay, the inverse of this function is quite complicated. So what are we supposed to do? There are some numerical approximations to do this, because basically what you're going to do is a kind of Fourier transform. But this is tricky because a computer cannot compute all the possible, let's say, frequencies allowed, because this is a continuous information. You're going to make like your computer explode with the amount of information. So you have to choose a cutoff here, threshold. But if you choose it, it's too high, you can add some noise in the function. But if you choose it too low, you lose definition. And there is another problem. Besides the cutoff, there is the amount of information you need. If you have a small amount of information, the function.
Ludmila, can I interfere for once? In this graph, like what is in X and what is in Y axis?
What is in the X? What is the? Oh, I'm so sorry.
Yeah.
So okay, in the X, we have different values of frequencies, and this is like a kind of wavelets information, you know, about this, like are functions that decay really, really fast in the end. And this is just intensity. It's just the model of the function, it's just intensity. Don't worry about this. Okay. So, so here, all right. As long as so in the end, in my paper, what I did was like, okay, let's check continuously how much information, how much of measures you need to reconstruct the function. And you can get really nice results as long as you increase it, but it's sensible to noise. The lower part here of the graph is basically saying like, if the function gets completely stubborn, you can not even distinguish anymore in the case of small amount and lots of each. This was not even a huge amount of noise. The function becomes, it gives us some kind of artifact. What we're seeing below here is cannot be considered a quantum state. There is some problems with negativity, like really bad. Anyway, but this was a function very simple, like we're supposed to have just like a straight beam splitter, like just one mode of an optical state. But what if we have something more difficult to do, or different kind of measurements instead of Homodyne detection? So what we have to do is basically numerical analysis. It's quite complicated. So in the case of my paper, I decided to use some semi-definite programming. It's a kind of convex optimization. You want to minimize some function, give some conditionals. There are a bunch of inequalities, and those all relates, for instance, with the representation of quantum states, some constraints. So we have the state has to be some identity has to be correlated with real, something that could happen in a laboratory. And I decided to use something called Fock bases to describe, instead of dealing directly with the Wigner functions, because, for instance, those Fock bases are related with reconstruction by wavelets. And this is very nice because it can be truncated really nice. And basically what I'm doing, it's this analogy, guys. It's reconstruction, like using a small amount of bits. Just to the smallest set I can do this, just to reconstruct just the right amount of information. I don't know, just identifying the state, just to know. For instance, you know, this is Mario, I guess your generation is not so not so young. But you can see, like, just with few information, you can show Mona Lisa, you can show Mario. The same can happen with quantum states. So, and this is easily translated in a kind of algorithm for instance, I've been working in the past with MATLAB. So you can basically use some software, the Mosaic, and some optimization routines, and this can be all those constraints can be added to the function, so you can calculate it. And if you want more details about this, please check my paper. Like, it's available on archive, so you can check for free. Don't need to worry about the magazines and stuff. Anyway, so why I'm worried about this? What's the deal about this reconstruction, right? Because it can have some kind of bias. No, what guarantees that your function, what you want to reconstruct, is going to give you something that makes sense? Well, for instance, in my case, we decide to just consider, like, okay, what I don't know, that it has the same equal probability. I want to diminish the entropy of the information in this case. So basically, of course, if you have some assumption about the state, you can use it as an input for the functions of numerical analysis. But if you know something, if you know nothing about this, it's better to just, like, okay, I'm ignorant. It has equal probability, everything. So this is one of the results of my paper, like the same reconstruction of the Wigner function. And the thing is, the small fixtures use the same set, same amount of information. The figure on the right is the usual algorithm called back projection algorithm. And as I said before, it introduces a really huge amount of noise and makes the function completely weird. And this is the thing I did, like, this is a reconstruction using basically the basic routine of my algorithm. So what do we care in the end about information, all the information about the quantum states or whatever? Because those guys are basically the foundation where everything you're going to do is related with the states, and those guys are very important to, I don't know, make some cryptography, teleportation, all the cool stuff, all the results from quantum computers came from very nice properties of quantum states. For instance, an entanglement, which was one of my preferred ones, and also for computation. This, I don't know if you guys know this picture here. It's Babbage and Ada Lovelace. Those guys have the whole concept about one of the previous old works on computations. And I believe, like, I used to believe in the past, like, dealing with continuous variable states, it could be a path to understand better about quantum computers, alternative way. This was an alternative application of computers that we know, because this is basically a mechanical machine to computer stuff, like analogically, not digital. I was basically inspired by this. And I think this is it for now. Let's open the questions. Thank you very much for listening to me.
Okay, yeah, thank you very much. So the thing is that maybe there will be many questions, right? And anybody, if you want to ask any questions, just unmute yourself and ask, or maybe you can post it on the chat. And thank you, Ludmila, for the talk. And okay, so I have the question, right? First of all, is that what is the Wigner function actually representing? Because I mean,
Okay.
yeah.
All right, let's go back a little bit.
Like okay, my question like this. I mean, I'm just layman in this, honestly. Like in the continuous variable, like Wigner function thing. But yeah. So I mean, what is this Wigner function actually doing? You know, like how it helps in the tomography stuff.
Okay, it's like because the translating the quadrature because like when you deal with continuous variable functions, I mean continuous variable states for optics, for instance, like let me see if I put the slide here, like because there's a very refined concept about the mathematics. Oh, that's here. It's the cat one. So basically, what is happening here is like there is a very natural correspondence between the annihilation and creation operators, mode operations, right, bosonic ones, and this position and momentum, right, operators. Do you remember something like this?
Yeah. I remember that. Yeah.
There is a very nice correspondence.
No, actually, there is a like the synchronization just left, you know, because I cannot see the slides. I mean, there is a problem. Yeah.
Okay. Okay.
Yeah,
but now you can see like just like the Homodyne tomography. The thing about using the Wigner functions because it's like this momentum, and I will go back a little bit.
Yeah.
This information about position and momentum is like it's inbuilt on the Wigner functions, part of the Wigner function, because the Wigner functions give information about the state somehow.
Yeah.
In this phase space, think about like in physics, where when we're learning statistical mechanics, when we have like phase space for a pendulum, in one axis you have like momentum, and in the other axis you have position, right?
Yeah,
it's pretty much the same. It's pretty much the same for quantum states. But the problem is like quantum states, as you know, like you have some impositions about measuring position and momentum at the same time, right?
Yeah. That's very
clear. As we know, like it's like a Heisenberg principle, let's say. And so like for a classical state in a classical phase space is described as a point inside of this phase space, right? Quantum states are defined by regions as an area. And inside of this area is like you have some amount of error, like it's related with the h bar over 2, something like this, right? Remember, this is like basically.
Yeah.
So, and the thing about the Wigner function, like when you think about the wave function, wave function, you have like position, and you take the Fourier transform, and you get the momentum, right? Yeah, the Wigner function is like something in between. As you can see, like for instance, I'm taking the function here, rho, and like projecting or when like taking the coordinates here, projecting of some kind of coordinates, and integrating over the momentum information, let's say. So you can get, so this object, the Wigner function, is related to give the both information at the same time, but with a price, unprecision. This area gives you a error, okay? And that's what also the maybe this negative information, this weird stuff comes on, because quantum states are very like some quantum states are more classical than others. For instance, when you analyze coherent states, for instance, they have no negativities, but they are very easy correspondence with actual laser, like a laser, pew pew, you know. So lasers are the best approximation you can have for a quantum state to a classical state. But the state here, for instance, the cat states is something very special, very unique. And also the whole set of Fock bases is also like very, very quantum-like. And the Wigner function is nice because of this. You can detect some kind of quantumness from these negativity values as well. So there is a lot of features. It's not a bug, it's a feature.
Yes, I see. Okay, so there is a question like, is there a set, I mean, is there a set number of times the measurement should be done to get a good estimation of the actual state?
Well, this
is asked by Akash Narayana. Yeah.
Okay, this is actually a very good question because it depends on the state. If the state has too many details, it requires more resolution, right? If you have just like just think about pictures, okay? Just think about, I don't know, a square, a black, a white dot of in the shape of a square in a black screen. It's quite easy to, identify this. But imagine something very, I don't know, the Mona Lisa itself, the lady in the beginning of the presentation. Like if I reduce even more the information here, we would be completely lost, because we basically see like a meaningless shape. But so in the end of the day, this number of measurements you're asking is a good question for also, let's say, experimentalists. This is also something that I'd like to ask us, because it's completely state related. Some states requires more information than the others. So this is a very interesting problem.
So, I mean, as you said, like this Wigner state has like more quantum than other states, like the coherent states, you can say. Is there any correlation between like the measurement we need to do and the quantumness? I don't know. I mean, maybe.
Probably, because like, for instance, like coherent states,
yeah,
I think they are basically Gaussian functions. Gaussian functions are more easy to handle. The actual is like Hermite functions and Fernando functions and all these complicated functions. So yes, I think it may be a correlation, but I'm not really sure, because you can, for instance, like, okay, one Gaussian function is fine, but when you combine a bunch of Gaussian functions at the same time, this can also be complicated, which is the case of the cat state. The cat state, I can, let's see if I can, oh no, let me share my screen again. I wanted to make some annotation. All right, because the cat state is something like this. It's a sum of some coherent state. So sorry about my letter. Sorry, guys. It's like a
it's a bit lagging, but like it is called, because when you say about cat state or something, like the cat concept was like superposition of like more than
Exactly.
So it is like superposition of Gaussian states or something. I don't know.
Yes, it's a superposition of Gaussian states. I think it's something like this. Let's say it's like I'm gonna put some normalization constant here. Okay, so basically it's a summation of two very
I think your screen froze.
Oh no! Are you listening to me?
Yeah, just say no problem. Yeah.
Okay, so basically what the cat state is kind of displaying with data or live, because you have like a convex sum between a coherent state and another coherent state, but with the signal is changed. For instance, like we have I don't know, some displacement value of, I don't know, 1, the other one is -1. So you're summing something symmetric states, I would say.
Yeah.
So that's the playing with the dating or live. It's cat state because people think about the Schrödinger, the guy from the Schrödinger experiment with the cat, so that alive. So that's it. And this is a very difficult state to produce in the laboratory. Just saying, like it's very sensible to the coherence problematic, but it's very nice. Like look at the shape. Look at this shape. I mean,
I cannot see anything, honestly.
You cannot see. Oh, come on.
My God. No, that's fine. Okay, and now I can see. Yeah. So, okay, so there is a question, like, if we don't know the number of times the measurement should be repeated, when do we stop the process? Like, how do you know that if there is a decent estimation of the output state? Is there any measure?
Okay, I think I'm not the one that what I was proposes like give me your data. And I'll try to give my best. Okay. Like this is the amount of data necessary. Like it's something that I made this algorithm here from people to use on the laboratory. Like you make some measurement scheduler and measure all the information that you think as experimental is necessary. So just give me your data and I'll process and I'll give the best that I can do it for you. That's the thing I want to say.
So I mean, I think like Akash, you can unmute yourself. I mean, if you want, unmute yourself. But I think it is mainly like, I think he's asking for like algorithmic point of view, because there must be like a cost function or something, like.
Yes, there is.
Yeah.
Yes, of course there is. And with this.
No, I mean, the question mainly is, I think Akash is asking like, in case of quantum algorithms, maybe we can define the cost function like, I don't know, I mean, quantum states and gates and this kind of stuff. But in case of this continuous variable stuff, this is like, looks very complicated, right? I mean,
yeah, but that's the thing about using, instead of dealing exactly with the wave functions and stuff, that's the thing about the Fock basis.
Okay.
The Fock basis is easily translated in Wigner functions, easily. And in the case of the phase space representation, as I said before, the signal could be reconstruction use this Fock states because they are actually wavelets. It's proven, mathematically proven, that the wavelets is like they can reconstruct a given signal with a finite set. But the size, as your friend asked, it depends what the information that the experiment is going to give me. But as you said, like the state, the cost of this function increases actually considerably, I would say, because as long as like you increase the number of the, I don't know, let's say Fock states, like you have your base increased by, I don't know, by the power of 2, right? Because this is basically reconstruction. What I want to say here is like, this is reconstruction. Actually, the output of my algorithm is reconstructing the density matrix of the function. Okay, but there is in the beginning of the presentation, there is the Wigner function. It has a direct representation with the density function. I think it's easier to handle if the density function truncated in the Fock's space than dealing with the continuous functions with a lot of Fourier transform to get it in a phase space. That's the trick about the algorithm. And the size of the reconstruction, the amount of information you can put it depends, of course, on your machine. It depends, of course, how much space in the memory do you need, it's available to use. So, of course, the bigger is the space, the bigger is the, I don't know, like the number of Fock states you're going to reconstruct it. Of course, you have more resolution. It's pretty much exactly the same like a video game and then bits information. You increase the amount, you have more information, you have more resolution. That's right. So the thing is not about this algorithm is to not overestimate stuff. Yeah. You have a small set of information. That's all I can say about it. All you can say, like this tiny amount of information, I'll try to give you. The other things, I lost.
Yeah. So Aritra was asking a question like, what's the final output from the QST, like this state tomography in continuous variable? Is it still a density matrix? I mean,
what do you mean?
Aritra, can you please?
Yeah. So when we do with when we work with like gate-based quantum computing, once you get the measurement results, you want to reconstruct back the density matrix from it. Okay. Right. So what's like the output in this case when you have like a continuous variable?
Okay. In the case of I'm going to get back to the Homodyne tomography. In the case of optical states, what you have, remember the double slit experiment?
Yeah.
Remember this? Like you have some areas of, I don't know, darkness and brightness.
The interference pattern, yeah.
Exactly. There's the essential thing about this is interference between the signal and the coherent state you're controlling. So you have variations on this brightness, the intensity, which is related. There is a proportionality between intensity and the photon number, right? Because if you increase the photon number, there is a bunch of photons hitting the photo detector. Basically, what you have is something bright, right? And this correspondency has something to do with creation and annihilation operators, right? Destroy amount of photons or creating more photons, so you have more brightness. And this also can be correlated with position of momentum of the electromagnetic waves. So that's why this comes from. This whole proportionality has something to do with this. In the people usually in optics you use this word quadratures. Quadrature is just this information about the position momentum and combination between like position momentum in the phase space. So basically the information what you measure here, the frequencies are brightness, light, amount of light.
So it's reconstructing the quadratures, we can say. I mean, in this
you
sense,
like from the amount of light, the brightness you have, it's related with some measure, it's related with some property of the position momentum of the electromagnetic wave. It's very, oh my god, like if you wanted to check the derivation for this, it's available here and a lot of article books, but I think it's out of the scope of this presentation. I'm so sorry guys, but basically like the result is this, like this n number here is like a number operation. I don't know if you know about this. As you can see, the number operation has something to do with the intensity of the coherent, like this intensity of the displacement of the coherent state. And this key stuff here is like key theta is like something between, like you have the, think about two axes, okay? You have the position and momentum axis. This key theta is something between this, pretty much like this random transformer I was saying in the beginning, like this projection in some point of this axis. This theta is related to this. So for instance, like when theta is equal to 0, you're just measuring the position axis. When theta is equal to pi over 2, you're just checking the position, momentum axis information. So
so I mean, Akash's question, something similar to that, like what you explained, like can you please briefly explain like how to go about estimating a state using quantum state tomography? Like let's say if you have a single qubit state.
About qubits.
Oh,
okay, when you have a qubit, you have another kind of measure actually. I guess probably like, because the whole thing about tomography, you're going to use like a complete set of information of the state. And for case of a qubit, this is good. I think one of the things people are being used just to project the state on the using poly matrices to project. For instance, like because like poly matrices gives like basically the entries of the density states. Combination of
like repeated measurements on the particular thing, right?
So basically like you're taking your state and projection in subspaces, like looking for the shadow, like for the vector and small in a different, I don't know, coordinate, in orthogonal coordinates. So you can get the complete information for this orthogonal set. It's this is more algebraic. For qubits, it's straight for algebra. Algebra. For this process here is also linear project. It's also linear. Everything is linear here because it's still quantum mechanics. But instead of using like it's being constrained by a small qubit space for the case of qubits, small. There's a lot of considerations here. Instead of this, you're going to use the continuous sets of position and momentum. So that's the only difference. Just change the algebra for insanely hell calculus. And
so this is like a continuous variable system. That means like not only one level or quantized level. It's like set of energy levels or something like this.
Yes, that's the thing.
So I mean,
just think like if the Wigner function is hard to think about because it's very abstract. Just think about the wave function. Wave function, like any value, like when you integrate make the integral of wave function times what's the name of this? Like there's a name of algebra for this, but basically like when you integrate the information you want, you're going to get something because we are talking about probability, right? It has to sum up to 1. This is the normality. The state has to be normal, right? It doesn't matter if it lives in an infinite space or it's just a qubit, 2-level states. It doesn't matter. But since we are dealing with probability, this have to be normalized.
Akash, you unmuted yourself. Would you like to ask anything?
Yeah.
Yeah.
I've got a question. I did a little bit of reading about quantum state tomography, and they mentioned something like you get take measurements from different bases. So using that, you can get different density matrices, and at the end, you can get a estimate using those the density matrices. So what is this different basis? Do you apply operators on the state, or maybe I mean gates on the states to change into different bases and take a measurement, or what is it? What's happening?
Well, it's because like in the end of the day, you can just think of, let's come back again to linear algebra, right? You can use different sets of bases as long as they are orthonormal to represent the same information. But the way they're going to describe it in terms of summation and stuff, it could be different. But in the end of the day, you have just the same information. It has to be normalized. So different bases, it could be, for instance, like I didn't mention, but this is the Homodyne tomography, but there's something called heterodyne tomography. So instead of measuring, for instance, quadrature, they just measure it, I think, directly on the Fock basis somehow. They have another set of measures to project the quantum states, but at the end, you're just getting the same information because the state, just using the fact that you're using like a different combination of bases, I think it's not problematic at all.
I saw something like you should do some set number of measurements and it should be tomographically complete something, the operators which you use, something like that.
Yes.
I didn't properly understand that. And
because
I was puzzled, how do you decide on these operators beforehand if you do not know the state which you're going to measure? So I was wondering how you go with that.
Just a sec. I think this question is very good, actually, because like as long your state lives in a bigger space, like for instance, like you have a qubit instead of qubit, like a q3, q-quart. I don't even know how to call them above 5 anymore. But as you can see, like the amount of information, for instance, the density matrix increases really, really fast. Do you agree? Because you need more entries in the density matrix, like each entry could be given by a projector. So like this is increased really, really fast, and this is a problem for any tomography because I think tomography is a complicated problem. So the best you can get to be information incomplete is a set of the size of the dimension square minus 1 of the state you want. So because like, for instance, like in the Pauli, for qubits, you have the Pauli matrices, right? You have identity, X, Y, and Z, and you make a bunch of combinations of those guys. For instance, the identity is not so useful. So you have like, a qubit has like, we have 4 entries. So you're going to use like with X, Y, and Z, you can reconstruct the information completely from the state because the identity was relevant. The identity doesn't give much information. Then we have 2 qubits interacting. So you have this square minus 1 again, because you have identity times identity for each state. So it goes. In the case of continuous variable states, it's impossible to get informational complete basis because their state is infinite by principle. You have infinite information to handle because it's infinite space. So everything you're going to recover is going to be incomplete by definition.